Welcome, guys. It is another beautiful Tuesday afternoon, and that can only mean physical sciences. My name is Tobile Nkosi, and I will be then your physical science teacher for this afternoon. Well, I want to send tons and tons of love to Liberty. Thank you so much for sponsoring the show. And truly, guys, none of this would be happening. Thank you so much for the opportunity that you've given us to help the class of 2021 with their final exam preparations. And grade 12s, if you haven't done it yet, please do download the Tenfold education app. It is an app filled with tons and tons of past papers that can help you guys prepare for your final exam papers. It has, well, the question papers as well as the memo, just to double check if you're doing everything right. And if you're wondering what question paper we're doing or you'd like to join in the conversation, please do send a hi to the WhatsApp number on the screen and meet Dex, which is our chat boy. And he can then send you the question paper that we're actually busy with today. Another thing or another platform, if you want to join us on YouTube, you are more than welcome to follow us. And on YouTube, we are then Mindset Learn. There's another platform where we can help you guys prepare for your final NCS. So in today's show, we will be looking at paper number 2, which is acids and bases. Now, acids and bases is a lot of stoichiometry all the way from grade 11. If you are struggling a little bit with the stoichiometry, please take your grade 11 book and then check it out. So without wasting time, let's see what question we have now. The question that we have here is question number 7. So most of the times, acids and bases will be question number 7. The question reads, learners prepare a solution of known concentration. Now, already, if you have already been practicing past papers, the minute they underline something or they write it in bold or they write it in big letters and so forth, the examiner is trying to catch your eye, or that certain or specific phrase actually means something very important. So of known concentration, by dissolving 2 grams pure sodium hydroxide crystals. And then they've given us the molecular symbol there, which is NaOH in water in a 250 cubic centimeter volumetric flask. Just want to highlight on this. Remember, every time we are working with volume, when we work in chemistry, especially in grade 12, when we work with volume, it has to be in cubic decimeter. If your volume is given to you in cubic centimeters, then you need to convert it to cubic decimeter by dividing it by 1,000. Unless you're using the titration formula. As we get to that, I'm going to continue reminding you. But already, this is a thumbs up where you actually need to convert, so keep that in mind. So number 7.1 says we must write down the term of the underlying phrase. And this is only 1 mark because this is some of the theory that we need to know. So a solution of known concentration is what we call a standard solution. We call this a standard solution. So that is 1 mark in the bag. Let's look at 7.2. Now we are asked that we need to calculate the concentration. We need to calculate the concentration of the sodium hydroxide solution. I want to go back to my question so we can actually highlight what we have. I have 2 ways of working this out. The one is actually a very easy, quick method. The other one, if you want, is a more lengthier process, but you also get exactly the same answer. So the first method which we can use, well, I've got 2 grams here. Remember, grams is the small m in a formula. In water, this is my volume. If I move my comma 1, 2, 3, this is 0.25 dm3, which is cubic decimeter, and that is then the volume that I have. I also know that I can find my big M, which is my molar mass that I can find on my periodic table. N will be 23, oxygen is 16, and hydrogen is then 1. So then that's all the information I have. So let's see if I can then calculate the concentration for the solution. The first method that I'm going to use, let me make a nice bubble around this one so you can stay with me, is this one. C is equal to M over big M. Remember, that's the mass, that is the molar mass, and then the volume in which all of this is taking place. We are given, or we are told, that it is 2 grams. So you're going to see everything that I'm going to use, I'm going to get in the information given. I have 2 grams. The molar mass, well, if we add all of this, I will use a calculator just to be sure. So I'm going to add the molar mass, which will be 23 plus 16 plus 1. Therefore, I get 40. So my big M for this formula is then a 40. I'm going to put everything in brackets. It just works so much better. And then V represents my volume, which I've already found. Remember, it was 250 cubic centimeters, which are converted to cubic decimeters by dividing it by 1,000. I'm going to put this in the calculator exactly as it is. I like putting brackets over everything. So that will be 40 and I'm going to have 0.25 on this side. And therefore, I get my concentration as 0.2. Now, it's very important that you write your SI unit. So for concentration, we have mole per cubic decimeter, right? Remember your SI unit, and that was for 4 marks, so that's actually quite some marks. Another way in which you could have done it, you could have first found your moles. So you could have said N is equal to small m all over my big M, right? Remember your moles. So my mass, I was told, is 2. My molar mass is 40. So let's see what I get there. I'm going to put everything exactly as it is once again. So that's 2 over 40. And I get 0.05. Remember, SI unit for N is my moles. But remember, they asked for the concentration. I have another formula for concentration, which is C is equal to N over V. So my moles I just calculated is 0.05. And my volume where it's taking place was 250 cubic centimeters, which we converted to cubic decimeters, and then I get 0.25. So let's do that one. So I get 0.05 divided by 0.25. And therefore, again, I get 0.2. 0.2, remember the SI unit for concentration is mole per cubic decimeter. So you want to add your SI units because you want to show the examiner you know exactly what's going on. So as we move along, in the start of the show, I'm going to, most of the time I'll do 1 or 2 methods because most of us don't actually think the same, or some other people have a different way of tackling a problem. You know, I'm more of the lengthier process. Some people have a shortcut and so forth. But as we move along, I'm just going to show you the introduction of how to, the second way of doing the equation, then you can just follow through so that we can actually do a number of questions. And then the next one says calculating the pH. So the pH actually has quite a number of calculations which you can use. So remember that the formula that we use for pH will be pH is equal to negative log. I want to start it the long way around so you know why I'm doing this. And that is H3O plus, right? But now they want the pH of the solution, and I want to just take you back here. The solution is NaOH, which is then a base, right? Which means that the formula that I'm using over here might not really work because when you talk about a base, then we have OH minus ions, right? So this means I must first solve for this. So I'm going to take it one step back. That's why it's for 4 marks. So the one way of doing it, let me just work here. I can calculate the concentration of this. Remember, H3O plus multiplied by the concentration of OH minus gives us 1 times 10 to the negative 14. Therefore, I'm looking for this one, because that's the pH that I must look for. You can see my formula is H3O plus. I do have that one. Remember, I just actually calculated it where my concentration was 0.2. So that's 0.2 I'm going to use. And NaOH is a base. So I'm going to keep that there, H3O plus. And this was 0.2. This is then just mathematics. 1 times 10 negative 14. To get the H3 plus by itself, I divide both sides with what is bothering it. In this case, it's the concentration of 0.2. Let me write that one properly. What you do on the one side, you have to do on the other side. On this side, this and this will cancel. Then I'm going to have the concentration of H3O plus. I'm going to put this side exactly as it is on my calculator. Remember to always put brackets, otherwise your calculator will do BODMAS first. So it's 1 times 10 to the exponent minus 14. Close that bracket, and at the bottom I've got the concentration of 0.2. That's what we just calculated. If your answer was wrong, you continue with the answer that you got in the previous question. I get 5 times 10 to the negative 14 as my concentration. 5 times 10 to the negative 14. And that is then mole DM3, because remember that is concentration. Now that I've got this one over here, I can therefore plug it in. Minus log, I'm going to put that concentration of 5 times 10 to the negative 14. Let's put this in our calculator. I'm going to get negative log 5 times 10 to the exponent minus 14. Now your answer should actually guide you whether you're correct or not. So I get 13.30. Remember, always to 2 decimal places. If the third number is less than 5, then it doesn't change the number in front of it. So I'm going to leave it as 1330. I just want to show you here something quickly. Your answer should actually guide you. Remember, when you look at a pH scale, 7 is neutral. We've got 0, and then we've got 14. On this side, it's more acidic. On this side, it's more basic. Our answer is 13, which is closer to 14, meaning it's on the basic side. I want to show you here. The solution that we're talking about is NaOH, which is a base. And if you get a pH that is greater than 7, it shows that it's lying in the pH scale of 14, which means the answer that we're using here is absolutely correct. I just want to take this one off. And I just want to write the formula of another one that you could use. Let me just write OR over here. Some teachers like using the POH method, which is POH is equal to minus log, and then the concentration of the actual basic solution, which is OH minus. So therefore, you're going to use what we have gotten. So once you find your POH, don't want us to waste too much time. You're going to use the formula pH plus POH is an equal to 14. So once you get the POH, you're going to substitute it there, and therefore you're going to take this to the other side, and then you'll find your pH solution. And then exactly the same, you will get the 13.30. So that's another way you can actually calculate your pH. Then here's a question. Already when you see a question for 8 marks or 7 marks, then you should already know they're looking for, the question is telling us about something in excess, or how much was used, or how much is left over, which means that is a number of stoichiometry. How I always teach my kids, always write the equation, write what you're actually given and so forth. Remember, and with stoichiometry, you're able to move from one to another only if you know your mole ratios. Right? It's fairly easy. Read the question properly. Worst case scenario, if you are really struggling, draw yourself a picture. When I started in grade 10, 11, and 12, I always used to draw a beaker and adding this thing in, and then it kind of made sense in my head. So you're more than welcome to use that method. But this question that we have here, it says, the learners now react 1.5 grams of pure calcium carbonate with 50 cubic centimeters of dilute HCl of unknown concentration. The excess, remember there's a difference between excess, limiting, reactant, and so forth. So excess means more than. The excess HCl is neutralized with 25 cubic centimeters of the NaOH solution they prepared. The balanced equations for the reactions are as follows. Just extend my page here. So I've got 2 different equations, right? This is the first one where I have the calcium carbonate with the HCl. But then they also say that the HCl is in excess, so they continue to use the HCl in this equation with the NaOH, right, to neutralize it, and then I therefore have a new equation. So I've got quite a number of things that is actually happening here. So what I would suggest here by the CaCO3, I would write the mass as well as the volume if you're given, and by the HCl, I'll write the cubic centimeters for the volume, and then the NaOH. Remember, we did calculate the concentration in the previous question. You can also include it there. Now they want the initial concentration of the HCl. So now, if you can think about it, the HCl worked in 2 different ways. It first neutralized the one, it was in excess with the other one, and then meaning we'll have to add the 2 so that we find the initial, right? We had something, it was used a bit for here, they used whatever was left over to neutralize something else here. If we found what was used in the first equation, and when we find what was used in the second equation, add that together, then we can find what was initially used. So think about that logically. So that's what you have to have in mind. So let's start with my 2 equations. I'm going to start over here because this is what, it doesn't really matter where you start, but in this case, I'm going to start over here because that's what was neutralized. So I'm going to have 2 different forms. So the one, I need to find the moles. So I'm going to say, I'm looking for the moles of the NaOH of this solution. I'm going to use the formula Cb and Vb because that is then my base. I calculated the concentration of the NaOH in solution in the previous question, which I got 0.2. If you didn't use 0.2, please continue to use it in this answer. You get continuous assessment. And remember, it was used in a volumetric flask of 25 cubic centimeters that we need to convert to cubic decimeters by dividing it by 1,000. So I'm just going to do this in my head. I'm just going to move my comma 3 times, 1, 2, 3, which means I'm going to have 0,025, and that's the volume. Let's put this in my calculator and see how much we get. Just move my calculator here. So now I'm going to find the moles of that. I've got 0.2, and I must multiply that with 0,025. I love putting brackets on all my stuff. I get 0,005, 005, and that is then the moles of that solution. But now I'm going to use, remember this is stoichiometry, so we're going to use mole ratios. It's a mole ratio of 1:1, which means that the moles of NaOH in comparison to the moles of HCl is a mole ratio of 1:1. This means if I need 1 mole of sodium hydroxide, I will therefore also need 1 mole of HCl. This means that the moles of HCl will be exactly the same. Of HCl will therefore also equal 0,005 moles, right? This means this is what is in excess. Because remember what they said? They used the excess HCl to neutralize the NaOH. So this is what was used in excess. Now we need to see, okay, now that we found the one part, how much of this actually then now reacted with the HCl? So this is now another part that I'm going to do. Let me just number these parts so you can actually follow with me. Now, if you can see, I moved from here to there. Now I'm going to move from here, going on that side. Exactly the same thing using mole ratios and using what I'm given. Now remember, I am given, if I can find the moles, I can say the moles of CaCO3. I'm going to use the formula of M over big M. Why am I using this one? Because I'm given the grams of calcium carbonate. Small m is for mass, which is 1,5. My big M is my molar mass. Where do I find molar mass? That you find on the periodic table. If I have CaCO3, remember calcium will be 40 on the periodic table, plus carbon will be 12, plus I've got 3 oxygens, each with a mass of 16, and therefore I get 100 grams per mole. So my big mass, which is my molar mass, is therefore 100. I'm going to put this in my calculator so I can find how many moles therefore reacted. I've got 1.5 and then I've got 100. And therefore I get 0,015. And this is my moles. Now I also need to work or use mole ratios with this equation right over here. Now I've got a mole ratio of 1:2. I'm going to do it the long way around so you know how I'm getting this. Moles of CaCO3 in comparison to the moles of HCl. This we get from my equation. If 1 mole will react with 2 moles of HCl, I just calculated the 1 mole of calcium carbonate, which is 0,015. I don't really know the moles of HCl. Mathematics, cross multiply. 2 multiplied by my answer, 1 multiplied by x. I'm just going to change it around, which means that x, extend my page a little bit more, which means that x will be, I'm going to take this answer, just multiply that by 2. I get 0,03. 0,03 moles. So those are my moles. So this was an excess. This is what was initially used. This was what, let me not say initially, let me just say used. Then I'll have another formula where I can break that up. I can therefore say used. So as you can see, I found what was in excess, moving mole ratios to this side. I found what was used to dilute this using the HCl, moved to that side. Now I've got 2 equations. Remember, they're looking for what was initially used. So now I must just add. It's always nice to have a nice formula for the examiner so that you are showing them that you know exactly what's happening. So we're looking for the moles of HCl the initial. Now remember, when we're looking for moles, I'm just now going to add. I'm going to use what was in excess and use what was used to dilute the first equation. I'm going to say 0,005 moles plus 0,03. Let's find my total. Okay, I already have 0.03 there. I must just add 0,005. And then I get 0,035, 0,0035 moles. So those are the initial moles. But what did the question say? They said calculate the initial concentration. But if you're here, you're almost there. Now I can move from moles to concentration. You can use this formula. You can say C. I'm just going to put HCl so that you show the examiner which concentration you're calculating for. C is equal to N over V. Our moles is 0,0035, and the volume in which it was used was 50 cubic centimeters, right? Dilute 50 cubic centimeters of HCl. I must convert the cubic centimeters to cubic decimeters by dividing it by 1,000. I can also do that in my head. I'm just going to move my comma, and then I get 0,05. So I'm going to put this in my calculator, and let's see what we get. Just cancel that. So I get 0,0035 all over 0,05, which means that my initial concentration, I get 0,07. Just see if I did that one right. Let me just add this one again. If I have 0,005 plus 0,03, 0,035. Yes, there's not two zeros there, so I just want to take this one away. So I get 0,035. That looks better. I just added a 0 there. Okay, let's try this one again. Let's find our concentration. So 0,035, there we are, divided by 0,05. And therefore, I get 0,7. 0,7, remember, it's very important that you put the SI unit for concentration. And concentration is moles per cubic decimeter. And that is then how we would have answered this question. I think this was the last question for this one. But nonetheless, this is the different parts of stoichiometry that you could have used. So you could have started with the top one and then go to the bottom one, or vice versa. But in your mind, always think about what was an access to use to this one and what was initially used to the other one. And then you are more likely to actually get the answer. Well, without wasting time, let's go for an ad break, and I will see you after the break.
No one ever asks why we do the weird things we do. Like, why once is never enough. Or doing 2 trips is just one too many. Why do we, before we use these, or say 5 when we mean 20? Why do we have second thoughts? And think that lift buttons make them go faster? Why don't we walk there? Cross our fingers, touch wood, and struggle to hide our true feelings. At Liberty, we want to know all the weird and wonderful things that make us human, because human beings, being human, are what we make financial solutions for. Liberty, in it with you.
Did you know that the Sahara Desert is only a little smaller than the United States of America? The Sahara Desert is the largest hot desert in the world. It is the third largest desert overall, behind Antarctica and the Arctic. The Sahara is huge, a mind-boggling 9.4 million square kilometers, fractionally smaller than the 9.85 million square kilometer surface area of the United States.
Welcome back, guys. We are back from the ad break. We are still doing acids and bases, which is paper number 2, and I am Thobile. I want to thank tons and tons of love. I want to show tons and tons of love to Liberty. Thank you so much for sponsoring the show. And truly, none of this would be happening with you guys. Thank you for the platform that you've given us, and thank you for the opportunity that you've actually blessed us with. And grade 12, please grab this opportunity by downloading the Tenfold education app if you haven't done so yet. It is an app filled with tons and tons of past papers that you guys can use for your final exam preparation. Remember, with subjects like maths and physics, the more you practice, the more you can actually see the tricks and trades, and the more you get better at it. And if you're wondering what question paper we are doing, please do send a hi to the WhatsApp number on the screen and meet our friend Dex, and then we shall therefore send you the question paper we are doing. Another platform where we are live and active is on YouTube. Please follow us there. And on YouTube, we are there for Mindset Learn. Remember to use every and any platform that is available for you guys to pass. So without wasting time, we're still doing acids and bases. This is another question that we are doing. Also question number 7. This is a 2019 paper. So 7.1 says, define a base in terms of Arrhenius' theory. So now remember, when we were in grade 10, we would actually describe or explain bases as being strong and corrosive and bitter and all that stuff. But when we get to grade 12, there are 2 theorists that we actually focus on, the Lowry-Brownstedt theory and Arrhenius' theory. So now when they are asking you specifically on Arrhenius' theory, is it a proton donor? Is it a proton acceptor? Does it form H3O pluses or OH minuses and so forth? So examiner wants to actually see whether you understand that between the 2 theorists, one says this and the other says that. So please make sure that you specify that, not just the grade 10 explanation. So according to Arrhenius' theory, when we're explaining a base, we know that a base forms hydroxide ions. It's always good to know the name as well as the spelling, as well as the molecular symbol. And hydroxide ions are OH minuses. And we've already seen how a base works when we were calculating the pH in the previous equation. So a base forms hydroxide ions in water. It forms hydroxide ions in water. Number 7.2 says, explain how a weak base differs from a strong base. Now, a question like this can actually come from acids as well. Sometimes you're asked, they'll tell you a reaction we use HCl and then maybe acetic acid. They're both acids, but there is a difference between a strong acid and a strong base. And what makes them different between weak and strong is actually how they dissociate. So the first one, when we talk about a strong base, remember it is for 2 marks, so I would actually have 2 different sentences to show the examiner that you know exactly what's going on. So a strong base, when we talk about strong bases and acids in chemistry, you want to show the examiner that you know exactly what is happening as well as the correct terminology. So a strong base, we don't say it deforms or so forth. We use the word ionizes or it dissociates. So we can say a strong base ionizes or dissociates. That's the correct term. Dissociates. And that is completely. Don't forget the word completely. So a strong base ionizes completely. And you can say and or however or whereas. And a weak, because you're showing the comparison. You're showing the comparison between 2 things. Oh, I can't talk and write. Let me write this one. Ionizes or dissociates. And not completely now, but incompletely, or you can say partially. So this is the important terminology that the examiner is looking for, where we say a strong base ionizes or dissociates completely, whereas and a weak base ionizes incompletely or partially. It means, yeah, it does, but not really or not quite, right? So this one says, write a balanced equation, dun, 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 and this one is for 3 marks. So if your balancing of equations is not really that good, I want you to go back to your grade 10 book. So the balancing of equations was actually introduced to us in grade 10. In grade 11, there was a little bit of balancing of equations when we were doing limiting and access reactants. And in grade 12, not so much, but they can just hoy it in there just to confuse you, just to spice up that paper a little bit. But if you are having a problem with balancing of equations, look at grade 10 work. So now the question says we must write down the balanced equation for the hydrolysis. Now this term we would have learned in organic chemistry. Now we know that a hydrolysis reaction is the addition of water, which is H2O. So I know that the hydrolysis of NaHCO3. So I'm going to add these two to water and see what happens. So I've got NaHCO3. Hydrolysis reaction means water. Let me just write my phases here to be on the safe side. This will be in an aqueous solution. Plus, I'm going to add water, H2O, which is a liquid. Now, here we need to figure it out on what is going to happen. Let me just use a different color. Now, I can see that I've got sodium on this side. I know that water can dissociate into OH plus and H plus, OH minus and H plus. Where am I getting this? Already we were just talking about strong bases and weak bases ionizing partially and incompletely. Now I can see that N can form a base with the OH. This means this substance here can dissociate to Na plus and then to HCO3 minus. So this means the Na and the OH can form something, and then this H and this H can also form something. So I'm going to start with the Na. I can form a base by saying NaOH. That is also then in aqueous solution. So remember when we talk about charges we learned in grade 10 as well when we did polyatomic ions. Now, if I add this H here, it doesn't come, I want to write it wrong, then I'll write it right. Then I'll do it right. HH, we don't do it like that. Two things that occur in physics. When we have two of the same things in mathematics, we say square. In physics, I'm going to put the two down there to show that I've got an H over here that is coming with another H to indicate that I've got two H's now. I'm going to say H2. And then I've got CO3, and then the negative, right, then disappears. It doesn't really disappear, but it gets charged, and then we don't have it anymore. And this is also then in aqueous solution. So this is some of the dative bonds that we actually did in grade 11. And this was then for 3 marks. This is a balanced equation that we have done. 1 Na, 1 Na. I've got 3 H's. I've got 1 plus 2 is 3. I've got 2 plus 1. I've got 3 and 1 gives me 4. 1 and 3 give me 4. And my equation is therefore balanced. So this one was fairly easy. This was actually a nice question for grade 12. Something to ease your mind off a little bit. So let's look at this one. Number 7.4 says, a learner wishes to identify element X. So when you are having to identify element X, number one, you need to look at the molecule that you have, and then you need to identify the charges, number one. And to identify an element, it means we're going to have to look on the periodic table. And how do we identify an element? One of two things, either the atomic number or the atomic mass. Atomic number is the element's position in the periodic table. Atomic mass is then the number of protons and electrons in the nucleus, right? So I can see that if it isn't a molecule like over here, this will represent the big M of this equation. If I can find something somehow here, I could use this big M to find X, since I cannot just identify it using the atomic number. So let's see what we have here. I need to identify element X in the hydrogen carbonate I'm given here. I don't know what X is. To do this, she dissolves 0.4 grams of this unknown solution here with the X in 100 cubic centimeters of water. Already I can see that my volume is actually very incorrect. Remember, volume must be in cubic decimeter. To move from cubic centimeter to decimeter, you divide that by 1,000, and that is then of water. She then titrates, all of this solution with a 0.2 cubic decimeter, that is the concentration of the hydrochloric acid solution. I can see methyl orange, which is an indicator, is used as an indicator during this titration. Now, it's all nice words when they talk about methyl orange, phenolphthalein, bromethyl blue, and all that stuff. But as you're reading the scenario, in the back of my mind, I'll start putting on or thinking about why was this indicator used? Because most of the time when we're doing acids and bases, there's a reason why a certain indicator is actually used. They don't just use it because they didn't have the other ones. So as you're underlining and as you're reading, I would already start processing to when do we use what type of indicator and what each indicator actually represents in an equation. So already keep that in mind. So the first question is pretty easy. It says we must calculate the pH of the hydrochloric acid solution. Now with pH, in the previous question, I showed you two ways of doing it. So now I'm just going to do it only in one. In this case, remember pH, the formula for pH is negative log, and then the concentration of H3O plus. But I can see, hydrochloric acid is actually, it's an acid, it's not a base. So I don't have to use the first method's one of doing it. I can just go straight in. And I'm told that this solution, 0.2 mole per cubic decimeter, this is concentration of the hydrochloric acid. I know when I'm calculating pH, I use the concentration. Another way you could have used this in chemistry, when we use solid brackets, that means concentration. So now I'm just going to plug in. I've got negative log, and therefore I'm going to just plug this in. I'm going to have the concentration of 0.2. So remember what I said about the pH scale guiding you with your answer. Let's see what we get here. Negative log, and that is 0.2. I get 0.7. So remember, if the third number is greater than 5, it changes the 1 in front of it to the next number. But already I've got a 9, so the 9 will change the 6 to a 7. So my pH will be 0.7. I want to just elaborate something. An acid, very, very strong. Let me do it here. 7 will be neutral. This will be 0. This will be 14. Anything closest to 0 is acidic. Anything closest to 14 or in this side of the pH scale is very basic. If your answer is 0.7, it is very acidic. And we know that hydrochloric acid is one of the very strong acids that we get. That's why it's 0.7, right? It's very far from neutral. So it means that my answer is actually correct. If your answer was greater than 7, then something was not right. You had to sit back and just relook at that calculation one more time. Let me just extend this. Okay, let's look at another one. So now I've got 7.4.2. It says I must give a reason. This is only for 1 mark. Give a reason why methyl orange is a suitable indicator for this titration. Now remember, guys, when they ask you about the type of indicator that we are using, certain indicators give you, or you are allowed to use them when you know that the pH is going to be something. For an example, if the pH is going to be less than 7, we have certain indicators that we need to use. If the pH is going to be more basic, then there's certain indicators that we're going to use. So in this case, methyl orange that we have used, this is because the titration, they did say they're doing a titration, right? This means adding an acid and a base. A titration of a weak base and strong acid. That is one reason that you could have given. That this is a titration of a weak base, Let me just write the word base there. Let me do it right. See, Tobile can't multitask. Weak base and a strong acid. And a strong acid. So that's the one you could have said. Or, looking at the pH, remember when we're doing titration, we always look at the end point. We can say that the end point will be at a pH that is less than 7. And of course the pH was less than 7 because it was 0.7, meaning it was closest to 0. So there are a few indicators that we have, and then you need to know why we use what we use. Or let's look at this one. Already I can see this is for 6 marks and so forth, so I know that it's going to get pretty interesting. So the next question says, at the end point, so this means once the reaction is actually complete, when she's completed whatever she wanted to see, she finds that 20 cubic centimeters of the acid neutralized all the hydrogen carbonate solution. The balanced equation for the reaction is as given. Now they are telling us that we need to then find element X by calculation, and then that is then for 6 marks. I'm going to show you 2 ways in which you could have done it. So in this case, I have information on HCl, which means I can move from the HCl moving to the unknown molecule. So let me tackle it like that first. Let me write this number 1, make a nice bubble around it so that everyone can follow. I'm going to start with my concentration. Remember why I'm going to start with my concentration? I did calculate my concentration here for my hydrochloric acid. If your concentration is wrong and you got something not 0.7, or in the exam you're not really sure what your concentration is, please do plug in the concentration that you got in the next equation, because you're showing the examiner not only, you're like, okay, I got it wrong there, but I do know that the concentration that I was supposed to get here, I actually need to use in this equation. So that shows the examiner that something might have happened there, but you know exactly what's going on down here. So just continue, carry it down, and then continue with your question. So the first one, I'm going to first find my concentration. Remember, once I can find my moles from my concentration, I can find anything in chemistry. I'm therefore going to say the concentration of HCl, that's where I have most of the information. I'm going to use the formula N over V. Remember, my concentration I calculated was 0.2. I'm looking for my moles. If you can find the mole ratio of anything, the stoichiometry is then very simple, because you can find whatever it takes. Then I can also see 20 cubic centimeter neutralized, of the acid neutralized everything. HCl is an acid, which means the volume of that acid will be, I'm going to change this to cubic decimeter. I'm going to move my comma 3 times, dividing it by 1,000, 1, 2, 3, which means my volume will be 0,02. This is just mathematics. I'm going to cross multiply. This is over 1. N times 1 will give me N. And 0.2 times 0.02, let's see what I get there. So 0.2 times 0.02, I get 0,004. 004, and that is my moles of HCl. But remember what I said, I need to use what I have for the HCl, and I need to move to my unknown molecule. I'm going to use mole ratios. I'm therefore going to say my moles of HCl, compare that with my moles of the unknown X attached to the HCO3. This is a mole ratio of 1:1. If there's no number, it's a 1, so it's 1:1. So I'm just going to write it here as 1:1, which means if my moles of HCl is 0,04, it means that the moles of the unknown will also be the same. I can therefore say that the moles of the unknown element with X attached to HCO3 will also be 0,004 moles. I'm not done. Remember, I need to find the X. So therefore, I'm going to use my next equation. I just want to do it like this so that you can see everything that I'm doing. I'm going to use this equation now. N is equal to M over big M. Now I found my moles, and my mass was given to me as 0,4 in the original equation. Here we are. Remember what they said. To do this, she dissolves 0,4 grams of the molecule with the X. So that is the mass of that unknown X, which means by this M over here, I'm going to put 0.4 all over. My moles are 0,004. Now I want to show you the trick on, well, not really a trick, but how I'm going to do this one. This is the big M, which is my molar mass from the periodic table. So I'm going to have X plus the rest. H is 1 plus, carbon is 12 plus, 3 oxygens each with a mass of 16. And let's see what that will give me. So I've got 1 plus 12 plus 3 multiplied by 16 gives me 51. Oh, that is, let me just do this again. It's 1 plus 12, there we are, plus 3 of 16, and then I get 61. So this is 61 grams per mole plus X, so this is 61 plus X, right? Remember, I don't know what X is. I must first go identify it, and I need the molar mass of X to identify it on the periodic table. And then the rest, my darlings, is just mathematics. Now I'm just going to cross multiply. I'm going to put all of this over a 1. So 0,4 times 1 will give me 0,4 equals. Now I'm going to multiply in. Let me do it the long way around so that everyone knows where I'm coming from. So remember, in mathematics, when you have a bracket, you must multiply everything outside the bracket with everything inside the bracket. I'm going to do exactly the same thing. So here I'm going to get 0,004x plus. Now I've got my 61 on my calculator already, so I'm going to say 61 multiplied by 0,004. And then I get 0,244. 0,244. Now I need to solve for x, which is an unknown. I'm going to take all of this, take it to the other side, 0,4. If a number jumps the equation sign, it becomes a negative. I think maths teachers will kill me if I said jumps. Like, numbers don't really jump. 0.04, but it is a rule of thumb that we use. Therefore, I'm going to have 0.4, and I'm going to subtract the 0.244. And I end up with this number over here. So on this side, I'm going to have 0,156 is equal to 0,004. Remember your x. Now I need to find x by itself. Remember, to get x by itself, you divide both sides with what is bothering the x. In this case, I'm going to have 0,004. What you do on the one side, you do on the other side. 0,4. This and this will cancel. And let's see what x is. Let me do it again. I'm going to have 0,156, 0,004. Let's see what we get there. Oh, I get 39. And if I am not wrong, 39 on the periodic table is then K, which is then potassium, which means the unknown element K is potassium. I just wanted to double check if we are correct. Let me take it from here. As you can see here, if we removed X, X has nothing attached to it. I just want to show you something, how you can actually double check your answers. HCO3. If I was to remove X, if this molecule dissociated, I'll have X, which will be 1 plus. Then I'll have HCO3, 1 minus. This is polyatomic ions from grade 10. I can see that it only is 1. This means that it must be in group 1 because it has the ability to donate 1 electron. That's why it has a 1 plus. And I can see that me getting K, which is potassium, in group 1, it also is 1 plus because it is in group 1. So our answer there is then correct. So you could have done it like that. I do have another way in which we could have tackled this question. So let's look at this one. Remember, there's a million ways of doing it. As long as the examiner knows exactly or can see what you were doing, then it is actually perfect. So the other equation that I can use, I know that I was working with an acid and a base, so I can use the equation for that. So this is a very famous one. I can say CaVa, which is the concentration of my acid multiplied by the base of my acid, of the volume of my acid. And then I can have the concentration of my base multiplied by the volume of my base, all equal to the mole ratio of acid is to base. Now I'm just going to plug in my acid, which was my HCl. My concentration is what I calculated in the previous one, which was 0.2. It was put in a volume of 20 cubic centimeters. In this case, I know that the centimeters will cancel with the one at the bottom, so I'm just going to use it as 20. Now I need to find my concentration for my base, which is the unknown with the X. So I'm going to leave this as Cb. I do know that the volume in which it was placed was 100 cubic centimeters. I'm also going to leave it as 100, and it is a mole ratio of 1:1. So 1/1 here. Now I just need to solve for my B. So this is pretty easy. 1:1, I'm just going to cross multiply. So that means I'm going to have Cb multiplied by 100, all equal to 0.2. Now, I always like to put this once in a calculator. I'm going to divide both sides by 100. What you do on the one side, you do on the other side. 100 and 100 will cancel. Then I'm going to be left with the concentration of my base. I'm going to put this in my calculator. The reason why I put everything all at once is so that I don't have to keep converting and, you know, to 2 decimal places and so forth the whole time and write big numbers. I can just do it once. I've got 0.2 and I've got 20, and that is all over 100. And therefore I get the 0.04, and that is concentration. 0.04 concentration, the SI unit, is mole per cubic decimeter. So now I found the concentration for the unknown. I'm almost there. Remember now, if I'm looking for the concentration, remember it is X attached to H, CO3. I have the concentration for that unknown. I'm looking for the unknown of X. I can use the formula. M is over big M and V. You could have done it the long way around, calculating N over V first, but I'm just going to do it once. Now let's plug in what we're given. The concentration to what I just calculated, which is 0.04. The mass that I was given was 0.4. Remember, that was what was dissolved in. This was 0.4 all over. Now my M, it is X of the unknown plus, remember what we have? Let me do it this way so that I'm going to do it the long way around. I'm going to keep this as M, and then the volume in which it was then 0.1. There's a volume in which it was, so now I'm just going to do some mathematics and then see what I get here. I'm going to cross multiply. So I'm going to have 0.4 multiplied by all of this. I'm going to just do that in my calculator. Okay, I've already got 0.4. Let me just multiply that by 0.1 and see if I am winning. Therefore, I get 0.004. So I'm going to get 0.004, and therefore that is then my M. But now remember, for your M, you need to get 61. Right, so that is the value for your M. I'm going to divide both sides with what is bothering the M, which is 0.004. See, 0.004. This and this will cancel, and therefore I'm going to have an M. So now there are various ways which you could have done this. Let's see if we get the same answer. 0.4 all over 0.004, and therefore I get 100. So this means it's 100. But remember M is the molar mass. I just want to do it here again. If we have X attached to a C, CO3, it is whatever X is, plus hydrogen is 1 on the periodic table, plus carbon is 12 on the periodic table, plus 3 oxygens of 16. So I'm going to have X plus 61. So with M, I'm going to have X plus 61 as the molar mass of this molecule over here, all over 100. Now I need to get X by itself. Again, just mathematics. So what I can do here, I'm going to take the 61 to the other side of the equation. So therefore, I'm going to say X is equal to 100 minus 61. Remember, if a number comes on the other side, let's rather not say jump, but if it comes on the other side of the equation sign, then it becomes a negative. So I'm going to say X is equal to, and let's see if we get the same answer. Ooh, could have just used that one. 100 minus 61. And again, I get 39. And I get 39. And therefore, remember, always leave a statement. Let me just work here. You want to show the examiner that X is 39, which therefore means it is then K. Now, in this case, the question didn't really say by means of calculation. They didn't say give the name or the molecular formula. Had they said just give the molecular formula, you could have left it as K. But if they did ask for the name, then we were going to write the full name out of this one. So this is the last question. I just want to go through on what we did here. So remember, we had to identify element X. I think, guys, the easiest way or the best thing that you can do to make this easier for yourself is to use stoichiometry. I remember how I taught my grade 11s. I always taught them, if you're able to move from one to the other using mole ratios, you can do it in one straight line, or you can actually break it up. But as you can see, even with the previous one that we did, if you have the ability to find the moles of the one, use the mole ratios, then you can find anything. But with this specific one, identifying element X, the most information that we had was from our HCl. It all started when we had to find our pH, which was 0.7, and then we had to calculate the concentration of this solution over here. And we got 0.2 for this concentration. But I actually moved from HCl all the way to the side. And as you can see in both equations, the same thing actually happened. So getting most of the information here, I moved all the other way to the other side by using my mole ratios over here. And then I used what I knew for this molecule here. Even if you just know the big M, it is fine, because once you have, remember, if you have N is equal to M over big M, if you have this one, which you can get on the periodic table, and they give you a periodic table, then you can use more ratios to this one. Then you only have one unknown, meaning you can find your M. So that's exactly what I did on this side. I found my moles for my HCl. I used mole ratios to find the moles of this one. So it means 1 mole of the unknown reacts with 1 mole of the HCl to get my products as both my reactants. Once I'd found my moles, I was therefore needed to find M. The reason why I found M is because if a molecule looks like this, from this equation I can therefore find M. I do know that X was actually added somewhere here as an unknown, meaning that I only had 1 unknown. And therefore that's just mathematics. Remember, when you get to this step, if ever there's both numbers on each side of the equation sign, you therefore can cross multiply. And rather do it the long way around. Then you multiply everything outside the bracket with everything inside the bracket. That we learned in grade 9. That's exactly what I did, and then I just solved for the unknown by taking this one to the other side of the equation sign, and therefore I solved for X. In this side, however, I did 1 equation and 2 actually by using this formula right here. If this one was much more simpler for you, then you're more than welcome to use this one. And then I solved for the concentration of my base. I already knew that HCl was my acid, and this was my base, and then me finding the concentration, I could therefore move backwards. Once I found the concentration, I found a formula where I could use the found concentration as well as the mass in order to find my unknown. Now, with stoichiometry, there is a lot of work that actually needs to be done. That's why paper 2 actually has less questions than paper 1. But what I would say, spend time in doing this and understand what is happening. Think logically about what is happening, and then you are able to move around. And remember, if ever you feel like you're getting stuck somewhere, find the moles of something. The minute you find the moles of the one thing, you're able to find the moles of everything. And remember, what I also see with some of my kids, if you guys do things pretty fast, then you don't really look at the molar masses correctly on the periodic table. So make sure that you analyze that correctly and try punch things twice to see that you actually get the same answer. You don't want to make silly mistakes and get penalized for doing the wrong thing. Thank you so much for joining me. I will see you next week.